Okay, thank you for the warm introduction. So before I start, I actually have a quick follow-up remark on my previous speakers because they mentioned that today for most of the traffic is encrypted. And unfortunately, I won't say that's the case for the optical layer transport. So today, most of the optical communication is unencrypted. So that's why, because most people still believe that a fiber cannot be tapped, and that's reserved for another topic from my colleague. And so today, I think it's a good timing just to talk about securing the optical network. So of course, you could still do the encryption on the higher application layer, but I will get to there why you need to secure your optical network. And also, the other thing is that I do have I do have a buzzword. So I know it's a technical conference, but I still have a buzzword, quantum, in my title. But I will get to there why it's called quantum secure, just because before you know this quantum secure, you first need to understand what is the quantum threat. And this is actually the quantum threat. Many people first time saw this quantum computer just like Joe Biden's facial expression. What the hell is that? Okay, so first of all, I mean, I learned physics, and also I had a higher education degree. I still spent a lot of time to understand what quantum computer is about, because for sure, I cannot use that for Windows, whatever, Windows 11, 12, whatever, 20. I don't think you can install Windows 20 on a quantum computer, not to mention to do any daily work. And also, it doesn't improve my gaming experience, because everyone told me that a quantum computer is very powerful, but it doesn't help my daily life. So the bottom line is that, unfortunately, but also fortunately, the quantum computer is not a normal computer. Why is that? Just because everyone, I think, in this room, everyone understands how a normal computer works, because you have an input, you have some algorithm, you do some operation, calculation, whatever, you got an output. And then you can manipulate, and you can do different combinations, functions, and that's how a normal computer works. But the quantum computer is a little bit spooky because it works on this quantum qubits, right? So the qubits has this superposition, and you know all this kind of quantum physics. But if you use that phenomenon to do the computing operation, it means that at the same time, you can operate all these superposition status at the same time. And the magic is that everything happens at the same time, okay? So it's like, you know, teleporting or whatever. And by manipulating, again, this quantum qubits and also superpositioning status, you can generate multiple outcomes with single inputs at the same time. So just in a short a nutshell, it's just more efficient, right? So then, of course, that's good. But someone, I don't know, just thought, hey, we could do something also to defactorize some of the cryptographic system. So one of them is well-known RSA based on the factorization, the big factors of prime numbers. And with the normal brute force, it is very difficult to break it. But one professor from MIT called Shor, he developed an algorithm which could be potentially used in a quantum computer to break any kind of this factorization-based cryptographic algorithm. So, but it's not really black and white, as I said, just because on the left chart, you could see that the bar is the qubits, so the number or the calculation capability of a quantum computer, and also the line is the time that it will consume to decrypt or brute force the RSA algorithm, right? So it's not really black and white. It's not like everyone said it's like instantaneous. It will still take time. But of course, on the right chart, you could also see this tremendous development of the quantum computer in terms of the qubits. So right now, I think with the IBM latest developments, you can achieve about 500 qubits. So mapping towards the left hand of the chart, it is still not so harmful to the RSA or any cryptographic system. But if you look at the trend, so on the top right corner of the right charts, some people call it Q day. Okay, so that's kind of a decisive day that a quantum computer could possibly break the RSA or any kind of asymmetric cryptographic algorithm within a manageable time period. Okay, so that's really the basic of today's quantum threats. Okay, so a lot of governments and also some the speaker on the morning session also mentioned about this NIS2 directive and also other kind of governmental regulations. So the thing is that for any cryptographic system migration, it takes ages. Okay, so for these quantum threats, we expect the same. So even though that today the quantum computer is not so that threatening, and also this is not me or any of those kind of security expert trying to make anxiety or paranoid. It's just because for most of the critical data today in our network, they have a certain period of classification or confidentiality time. So it means that for the potential attackers, they could store the data today, and after 20 years, once the quantum computer is really available, or this quantum algorithm could be available to be used or abused, it will be still causing threats to your data that they store today. So that's why you will need a big cycle and also time to prepare and migrate your current cryptographic system into this quantum safe domain. So regardless of the application layers, so everywhere. So that's why we could first look at our today's cryptographic implementations. So you might pick up some of the words that you're familiar with, maybe from the very right-hand side. So the RSA, elliptic curve, and also AES. So all of them are based on mathematical models or mathematical algorithms. So it's why it's called computational security. And on the left, and also in the blue circle, you could see some of the information theoretical security, like the famous one-time pad. So everyone should know one-time pad if you follow Shannon or if you know communication, because Shannon really made most of the theorem for our today's communication. But also some red terminologies like quantum key distribution, post-quantum cryptography. So these are really made and also proposed today to mitigate and also to counteract this quantum threat, but in different manners. And also I already crossed out like RSA, Diffie-Hellman, and these are the potential under-risk cryptographic implementations today. So we need to move a little bit towards the left to prepare ourselves in this well-isolated quantum-safe cryptography realm. And also, there are more than post-quantum cryptography and a quantum key distribution in this area, like physical layer security, network coding, but these are either very early research stages or for some other different topic discussions. So today, I'm going to just focus on quantum key distribution and a post-quantum cryptography, because these are mostly interesting for both academic and also industry. So before diving into the details, so I still want to use this CI trials to emphasize what the communication security is all about. So confidentiality, probably that's the first popping up out of your mind, that you need to protect your data. But actually, and also all the cryptographic system is helping you on the confidentiality. But a secure communication is not only about the confidentiality, but also integrity and also availability. Especially the last one probably is even more important for the people here, because we're making networks. If the network is interrupted or the network is cut, probably the consequence will be bigger than the data leakage. Or maybe I shouldn't make that analogy, but for us, both are disasters, right? So that's why both of them should be seen as critical to the same extent in our holistic communication security. So now, first the question, is quantum key distribution ready? So perhaps, I don't know how many of you really heard about the name or know about the concept of quantum key distribution. I try to explain it in a very simple way, because Richard Feynman said that if someone could explain quantum physics, it means that he doesn't understand quantum physics. So I try to pretend that I understand quantum physics, so I cannot explain what's behind it. But anyway, so in short, the quantum key distribution is based on the phenomenon in quantum physics called non-cloning theorem. So probably you heard the story, Schrödinger's cat, because if you open the box where the cat is sitting in the box, that it was the poison on the one side, it was on the trigger, and on the other side is a pill. So before you opening the box, it's either dead or alive. But once you open it, the cat will be dead or alive. So the point here is that a quantum status or a photon is always or could be coded in this superposition, like I said for the quantum computer. But once you observe the status of that quantum bit or a photon, the status itself also collapsed. So that's kind of physical terminology. It means that you either just let it go, but not tapping into it. But if you do, you just lost all the information. So by itself, it's non-cloning, so you cannot repeat it. So the quantum key distribution, in whatever implementation, it uses this physical law that the bits or the data cannot be really copied. But then the point is that by today's communication or implementation, quantum key distribution could be seen as a very low-speed photon communication that cannot be copied. So initially, the quantum communication based on this this sort of implementation was meant for communication, but the speed was too low that almost useless for today's any communication because it's only kilobit per second or megabit per second. So some physicists thought, hey, why don't we use that only for the key distribution, not for the data? But that's really the problem. It makes QKD, okay, so I try to be a little bit provocative. So it makes QKD just not fundamentally secure if you think this way. Because why? Again, back to my initial idea. So the security covers a lot of parts: confidentiality, integrity, resiliency, etc. QKD only solves the one piece of this equation, the secure key. It doesn't transport data. It doesn't do the authentication, not to even mention protection. Itself is so sophisticated and vulnerable. So that's why it just provides itself as an unbounded attack on the photon itself. But if you don't do this one-time path, again, Shannon's law or theorem about the one-time path, by itself, it's actually not fundamentally secure or information theoretical secure. And also, most practically, the QKD protects or provides the keys in different implementation methodologies, but it lacks security quantification and also measurable metrics. So in this room, probably many people understand like a packet loss, error correction, or correct arrows, incorrect arrows. But in the QKD world, there's no such a measurable metrics. Some people talk about key rates, but if the key rate is like a 10 bit per second is good enough, or maybe 1 kilobit per second is good enough, there's no such a standard to define whether the QKD is good or bad. So that's another issue. And of course, you have these trusted nodes that the photon cannot be amplified just because, again, that's the non-clone theorem. So in practice, it is very challenging to build all these QKD networks. Okay, so it's really about another angle of security implementation. So here it's a little bit boring, but also important is that how the governments, and especially this related to the security piece, so how the governments perceive this QKD stuff. So if you haven't read this report, you could also search on the internet and you can download. And also I would point out that this positioning paper was also made and also endorsed here by Swedish Armed Force. And also together with BSI, the Dutch cybersecurity agency, ANSSI, so that's the French security agency. So BSI is our security agency back in Germany. So sorry, I forgot to mention that I came from Germany. So it points out that why QKD today is not mature. And I just listed a few. So first of all, there's no standardized protocols. And also there's no security proofs today. And also the evaluation methodology is also missing. Like I said, how you define which is good and bad, what is sort of the threshold of different parameters of different QKD implementations. So there are many things is missing. But also, I would say QKD is really controversial because, you know, the entire security industry today is very, very conservative. And especially, we learn too many hard lessons. So to one extent that we always want to use the latest and also the best breed technology to secure our network, but on the other side, we don't want to expose ourselves to unknown. So QKD today is relatively unknown because it has a relatively short development time, and also it creates a lot of different, I would say, new territories in security definitions. So I just pointed off, again, a few from BSI again, so the German Cybersecurity Agency, the UK National Cybersecurity Center, NSA in the US, and also ANSSI again. So all of them, they say, okay, guys, I don't really want to discourage you from research and investigating QKD, but just hold on a second, not to use them immediately, okay? You can do something for fun projects, you know, hero scientist, scientific experiments, but not touch the real production network, because there are so many things that we don't know about it. So that's why I try to cover like some of the key takeaways from the QKD today is that it's a partial solution because it only delivers the key, not the others. And also the other is like end-to-end security, the physical layer, equipment added. Last thing that which is still good is that if you are so paranoid, you can always add this QKD to further secure your key exchange. So that's a complementary physical security. That always holds true. Okay, so then furthermore, it's like, for example, BSI also made another report end of last year just to give some senses and also some views how to analyze the implementation attacks. Again, just because QKD is a completely new sort of technology solution and a new hardware, software piece, so no one really knows how to evaluate the security level of the device itself. So BSI made a very comprehensive, and also with our contribution, how to define the attack scenarios on the QKD. So as you could see that it's really the early stage, really the early stage to define a security product. And at the same time, standardization and also certification authorities are also gathering the information from both academia and also the industry, like in ISO, IEC, ITUT, Standardization Group, and ATSI in Europe, and also CEN. So all of them are trying to make some attempts and also sort of initial steps to define and also to sort of specify how a QKD system specifies. Nevertheless, I want to just make some comparisons. So on the one side, probably everyone knows about traditional optical communication today. And as I said, QKD is another type of optical communication, not really based on the pure line, but on the photon. And this thing, so that was probably the very first 40 gig and coherent transceiver back in 2008. And that's the time probably for me just going into the college. So I didn't even know about that. But after almost like 15 years development, today everyone knows this pluggable module, right? It's so simple, it is so powerful, but also it's very small. So just from the size, power, that you could see the development of the optical communication, but at the same time, so that was the very first QKD prototype by ID Quantic, developed back in 2008, about the same time, and that's also the inside of that box. And today, if you look at the QKD market, it's almost the same. Okay, so maybe there's some things that are miniaturized and also optimized, but basically on the technology side, there's probably it's again a little bit not so objective, but there are a little improvements on the practice and also on the actual implementation, but it's really for a future development. Okay, on the second part, what is the post-quantum cryptography? And again, this is a pure software and also mathematical algorithm-based solution, and similar to how the RSA and also AES was developed back in the NIST standardization group. So NIST standardizes most of these cryptographic implementations. So it also has a very long history, so or a long time period of the project. So from the submission of different new algorithms to counteract this quantum computing threat until the time that it's finalized and also it is evaluated by not only the expert group but also the entire world, just because everyone, any group could propose some counteracts or comments to those proposed algorithms. So after almost, again, 10 years research and the development of the project, so just a few months ago, NIST first published the first set of the post-quantum algorithms for both key exchange and also digital signatures. And also the European Commission or the Europe also encourages and also trying to harmonize the approach in Europe as well. So not to exactly taking the approach from the NIST, but also on top of that, and also to have this technology sovereignty in Europe, that we should also develop and also specify the post-quantum algorithms used in European member states. And some of the details, I don't want to go further, but there are a lot of different algorithms, basically, that's code-based encryption, lattice-based encryption, which was defined by NIST 2 months ago. And also the third bucket is called super singular isology key exchange. And especially the last one was an example that how this project or this sort of standardization project evolved, because it was broken and also found flaw during the middle of the development. And this is the way that this kind of algorithmic-based implementation developed in the standardization group. And also, many people concerned about this sort of large public key size from some of the code-based post-quantum algorithm. But for optical communication, this is not really an issue, just because the public key can be really acceptable for the optical transmission, because anyway, we need a longer size for the high-speed data packets. So this is sort of correlated. But then the point, similar to the QKD, it's not really bulletproof. Right? So we learn from also the past that you are not only facing the brute force attacks for different algorithms, but also mathematical attacks. So for instance, like this sort of SIDH, so the singular isology Diffie-Hellman algorithm was broken by the mathematical attacks, but also you have other implementation attacks, like the very famous side channel attack. So it's a very high, complex and dynamic environment, which also creates some uncertainty to the cryptographic industry. So that's why, for example, BSI defines a different approaches than NIST. So instead of having a single post-quantum key exchange algorithm, the Crystal Kyber, right now is named as MLKEM, Modular Lattice-Based Key Exchange Mechanism. BSI also defines classical McAlice, Frodo-KEM plus the MLKEM. Similar, ANSI has the similar approach, so not only taking the Crystal Kyber defined by NIST, but also adds the Frodo-KEM, it's unstructured lattice-based algorithm defined by BSI. So as you could see that there's a little bit discrepancy or different sort of perspectives between the European Cybersecurity Agency and also the American NIST standardization group. And then lastly, so how would the practical deployment look like if we just have all these things to put together? So first, again, just to echo what has been mentioned also to from my previous speakers, so you always have different layers of encryption. So it's not really black and white or bad or wrong, or bad or good that you should encrypt on this particular layer. If you're deep pockets, you could encrypt everything. But here, what we more focused is on the optical layer, so the layer 1 encryption. Because for most of the wholesalers and operators, like Netnod, if you provide a connectivity, you also want to secure your infrastructure, not solely relying on your customer side of security management. And also, what we do here is really the key takeaway is that the hybrid key exchange is the key itself, or it's a pawn, because the thing is that we don't really know. So one thing we know that in certain time that most of the conventional cryptographic system will be broken, like the Diffie-Hellman. So we need to do something to add on top of that. So now we have the post-quantum algorithms, and we have not only one, but multiple. So we try to add those post-quantum algorithms together with the conventional key exchange. But then also we have this very exotic implementation, which is QKD, completely a physical interface to deliver the key. And we add that as well as another a line of defense. So it doesn't mean that for your future cryptographic system that you need to choose one or another. You can basically have all of them. And it means that the final key that you used for the AES encryption is not it's neither one of them, but it's a derived and a combined key from 4 of them, it means that if one of the algorithms or one of the implementations fails, it doesn't really expose your key that are used for the actual encryption. So you have multiple layers of defense in this regard. And also for the QKD, so you require the trusted node, so it adds also another sort of layers of your fiber infrastructure. Of course, you could also do satellite, so that's also a very hot topic in Europe. So you could also trust, or you could probably trust the satellite more than the terrestrial trusted nodes. But either way, it adds not only cost, but also the complexity for the entire network. And also, of course, what we do here is to help the customers and also the operators to get approved from the governments, whether you do this common criteria or if you want to handle restrict data in EU or for NATO. So our focus is really to get the approved from the government side and also from the authority agency sides. And that's for the real application, but also on the research, we're helping this so-called EuroQCI. So we're engaged with almost half of this member states consortia and try to provide this encryption layer for as like a use cases for the quantum key distribution. Like one of the examples in France is that we want to build this sort of terrestrial trusted nodes for the tier 1 operator, Orange. So it's a very complicated setup. As you can see, it's the real sort of implementation. Back in Germany, we're working with Deutsche Telekom, and we try to build a link from Berlin to Bonn with almost 18 trusted nodes along the line. Again, it's not really for a sort of a production operation, but rather a lesson learned how to manage all these trusted nodes if you want to implement QKD. And also, lastly, we have a very first commercial pilot network operated by BT for this London quantum secure metro network between the two open reach data centers. And so basically the customers like EY, HSBC, those banks, they could just subscribe this managed security services, like subscribing the services from Netnod here, but this is quantum secure just because we have everything placed in the field that you only need to get a connectivity. Everything is secured on the optical transmission. Of course, you could still add your own user or customer, let's say, application layer encryption on top of that. That's your own choice. But the point is that for the infrastructure itself, it is completely secure and also quantum secured. So as a summary, as you could see that securing optical networking is getting more important just because fiber is also at a risk towards certain attacks. And a PQC will be the standard way, and a QKD is always a complementary solution and also a very interesting research front end that we are also engaged with. And also, of course, in terms of the infrastructure, operators usually are not really happy with messing up the transport networks. So again, to the point that a PQC is relatively easier to migrate. The QKD, of course, adds, let's say, extra confidence, but also it adds the impact to your network. Hybrid key, so that's the key takeaway if you forgot everything. So hybrid key is really the takeaway that you should foresee your future cryptographic system. And also about the research, standardization, commercialization, this is a huge topic not only for us, but for the entire industry and even the academia. So with that, thank you for your attention.